Good morning. We are moving ahead in chapter 5. We've looked at static friction, we've looked at kinetic friction, we've done a number of examples, and I hope everyone is it's kind of fun to be getting more developed models for how motion works. So we've included frictional forces. The last example we looked at was this person skiing. Doing a quick review here, we paid special attention to how the gravitational force was being divided into components, and that was kind of the biggest item that had come up. And so we did a force diagram with this. Again, the diagram here is showing how we've taken the coordinate system, the horizontal vertical coordinate system, and rotated that to create a new x, y coordinate system that now aligns with the slope on the incline. So for objects on inclines, almost always, not always, but almost always it's going to be easier and more convenient to set up a coordinate system that aligns with the incline itself. We went through and we looked at the two directions, x and y, directions along the incline, directions perpendicular to the incline, and we're able to go in and solve some examples here of looking at calculations of coefficients of kinetic friction. All right, and again, this was covered in the last lecture, and so I just wanted to have a little bit of an overlap there. So let's move on. Here, again, we've got an incline. So you can see these problems just keep getting more interesting, right? Here's a problem. We've got two objects with masses, m1 and m2. One of these, at least, is at 10 kilograms for its mass. We have one of those frictionless, massless pulleys that doesn't have any kind of an effect on what we're looking at. And so we've got an incline, and the incline angle is at 37 degrees. So what we want to do now is take a look at these objects. Now, what they're calling object A, they've got a couple of diagrams here. Now what they're doing is they're looking at two possibilities here. One of the possibilities would be they are looking, first of all, at static friction. So one of the possibilities is when we look at this setup, if there's enough static friction, the blocks won't move, right? If there's enough static friction, these blocks are gonna stay put right where they are. And so that's what this is asking about. It's asking about the coefficient of static friction. It says the coefficient of static friction is at 0.40, kinetic friction is at 0.30. It's the same 10 kilogram block, so we've got a lot of the same numbers we've been looking at. But let's see how the force diagrams would compare. In either of these cases, this mass hanging off the side of the pulley, object B that they have here is going to have a tension lifting it in this direction, and there's going to be a gravitational force downwards. And for the situation where the objects are not moving, if they are not moving, then these two forces are the same thing. So those two forces, they're going to match if the acceleration is 0. Now, there could be a constant velocity here too, but I think because of the static friction, we're really thinking in terms of the objects are not moving at all. So now if we look at the block that's on the incline, what we're going to see here is we're going to have a gravitational force component. The mg sine theta is going to be downwards along the incline. There's a tension pulling upwards, and it's possible that the static friction force is in this direction. So a static friction force in this direction would be preventing it from sliding down the incline. So that would be the case where the tendency here would be for the object to slide downwards, and the static friction is holding it in place. Now down at the bottom here, we've got the gravitational force divided up into the mg sine theta and the mg cosine theta, which we've worked from before. Now over on the diagram on the right, very same diagram, except notice that the frictional force is in the other direction. Gravitational force has not changed, normal force has not changed, but the tension has not changed, at least the direction of the tension. But the static frictional force has reversed. Now this would be the condition where the tendency is for the block to be sliding upwards, but the static friction is holding it in place. Now what they're showing in this example, and this is a really good thing to think about, I think this ties in pretty well with our intuition. It looks like they're leaving mass B as kind of a variable. So we could think of this in terms of mass B. What happens if mass B is really small? What if MB is really a small value? Well, if MB is really small, there's not going to be much tension here. And that means that the object, the heavier object, possibly, I'm speaking in relative, we'll be able to put some formulas to this in just a minute, but let's talk conceptually what we're expecting. I'm guessing there's going to be a low value of MB in which this would tend to slide down and the static friction is holding it in place. It could also be that there's a value of MB that's really large. Now if the value of MB is really large, so large, that the tendency would be for MB to create enough tension to pull the block upwards along the incline, well in that case I would need the static friction to prevent it from going uphill. So I'm thinking of this as kind of my low value of MB would give us a diagram like this. A high value of MB would give us a diagram like this. Now, it sounds like maybe it's a lot of bother because the problem has different possibilities going on. How could we simplify the situation so we don't have to completely solve the problem twice? So we want to take advantages of whatever is going to be similar for both of those situations. So I redrew this, and of course I relabeled these as M1 and M2. And then I drew the diagram for M2. Now at rest, the tension in here will be M2G. If it were accelerating, that wouldn't be true. But because it's at rest, the acceleration is 0, and because the acceleration is 0, the tension will equal M2 times G. So depending on how large M2 is, we'll have different tensions in the string. So there's going to be a tension in here. Now, what are the other forces that are going on? Well, there's an mg, that's an mg, I know it doesn't look like it, but it's m1g sine theta. So the way tension would work is the tension either needs to be m1 sine theta plus an additional static frictional force, if the frictional force is directed downwards. What would happen if we reversed that and it would just say, change the sign in one location? So what I can do is I can work with this one formula with a plus or minus sign, where plus is if M2 is really heavy, and minus is if M2 is really, really light. So that can take both possibilities into account. Now, there are no accelerations anywhere in this problem. We're asking what are the conditions such that M1 and M2 do not move, and M1 was given as 10 kilograms, theta is given at 37 degrees, the static coefficient of friction is given as 0.40. And so what we have here then is this picture. So we set up the forces, tension, gravitation component, and friction in one of two directions. And then what we did is we wrote down the expression for the static frictional force. Now, the static frictional force, if you remember from last class, can be represented as mu sub s, and I'm surprised I didn't write out the details of this, but we have done it a few times already. The mu sub s times n, and n is equal to m1g cosine theta. So if I combine that, this is mu sub s times the normal force, and the normal force has to match m1g cosine theta. So that's where that expression is coming from. And I would say when you're doing these problems right now, and you're just, this is new, you're just learning it, I would talk yourself through each step. Once you start to really see the shortcuts, then it will go faster. But often, students will just kind of try and remember a bunch of these formulas that maybe only apply to a few certain situations, and that's really hard to do to keep everything straight. You'll end up using something in a wrong situation. So again, I would say start by calling this the frictional force, and then go to mu sub s times n, and then look at the diagram and say n equals m1g cosine theta. I think it's good to break it down into steps and talk yourself through the steps each time an example comes up like this. All right, now the tension can be replaced by m2g, and so we just plugged everything in. There are no accelerations going on here. This is just straight, these forces balance out with these forces have to equal these forces. And so we ended up with an m2g equals m1g. Now notice, these can be combined. We saw that in some examples in the last lecture. So I'm factoring out the m1g. In fact, the g's cancel out. Now what does it mean in a problem when g factors out and it says whatever we're solving for works the same regardless of the gravitational field? So whatever we come up with will work the same if we go to the moon and we set up the very same, or we go to Mars and we set up the very same setup, a couple blocks on this incline. The formulas we get are independent of the local gravitational field. Okay, so the g's did cancel out everywhere. And that says the condition is that m2 needs to be equal to m1 times the sine of 37 degrees plus or minus 0.4, that was the coefficient of static friction, times the cosine of 37. Now, calculating the two values, what this says is if I put the minus sign in, the limit for sliding down is at 2.82 kilograms. And that's saying that m2 needs to be at least 2.82 kilograms. If it's not that heavy, the static friction will not be enough to prevent m1 from sliding down. So it does turn out that with a static coefficient of 0.4 at a 37-degree slope, friction alone, the static friction alone, is not going to prevent this block from heading down this incline. So that's something that we've established here, and it does require at least this much mass in m2, generating some tension here, to help hold m1 from going down the incline. Okay, which is kind of cool, right? We've done all this analysis, we've put all the numbers in, and we're finding out that yes, I'm going to need 2.82 kilograms here. Now at the other extreme, the value I ended up with was 9.21. Now what that's saying is, if I go beyond 9.21, there is going to be so much tension set up in this string that this block is going to go up the incline. The friction, the static friction, will not be able to hold it back. So it says for any range of m2 between 2.82 and 9.21, that will allow the blocks to stay at rest. So the no acceleration, but also no velocity coming into that. Okay, so again, that's that's kind of fun to think that we can come up with this sort of a determination, we can make predictions for what range of values will work and what range of values might not. Now here is a part B that I believe I added this in. I don't think the original problem had this, right? I take it back. See, this is reading the problem. So remember step one, read the problem carefully, and I didn't. There is a part B, and the part B says if the kinetic friction is 0.3 and MB is 10 kilograms, what would happen? So now that's a fair number of differences here that we've got. So let's get everything set up, kind of the same as before. Now, what is that going to change in the problem? Now, I haven't done a complete force diagram here. I didn't get the normal force put back in. I didn't get m1g cosine put in. But what I did do is I put m2 and m1 are at 10 kilograms now. Now remember, if we go back to part A, this apparently is all part A. And what we found was anything beyond 9.21, this block is taking off. Okay, and it's going to, M1's going to slide up the incline, M2's going to drop over the edge. It already is over the edge, it's going to drop vertically. And so what they're saying is, okay, this thing is now moving, and we're expecting it will accelerate. The forces are no longer balancing, and so we're expecting some kind of an acceleration. So what's going to happen in this case then, the normal force and the vertical stuff, or the tipped stuff vertically, that's working the same way. The static friction is being replaced with a kinetic friction force at this point. And that kinetic friction force is given by mu sub k times n, and that gives us the n, the normal force. If we look on the page before, m1g cosine theta, that's still going to work. And so we'll make that substitution in. Now, before we were just setting forces equal to forces, but now we've got an acceleration, which complicates things a bit, right? Now we have to look at the sum of the forces, and we have to divide through by the masses. When everything was just sitting at rest, we didn't have to go through that divide by the mass stuff, but now we do. So the acceleration will depend on m2g is driving this, that's the largest force here, I guess, minus m1g sine theta, and then minus the kinetic force, the force due to kinetic friction. And then this is going to get divided by m1 plus m2. So that's the net inertia, and up above is the net external force. Now, I calculated these all individually. Sometimes it's good just to stare at this. And so the driving force downwards, m2g, is 98 newtons. The m1g sine of 37 degrees, is this 30 or 37? Now I'm starting to worry. I think I put 30 degrees in. I think this one might be incorrect. Yeah, this is at 37. I've got to go back and double check numbers. These numbers are going to be suspect, so be careful with this. I should go back and get the notes corrected on this one. I'm just see how this turned out to be half of this number. That means it's the sine of theta. I think it's 30. I think I put 30 degrees in instead of 37. I will double check. So this could be off a bit, but for the numbers we do have here, if this were at 30 degrees, then this would be 49 newtons. The frictional force, oh, that's going to change too. So I'm going to have to go back and check both of those numbers, because that's also has a theta dependence in it. So double check these and see how it works. See if I'm using 30 degrees or... Anyway, so we're going to take the net force here, and we're going to divide through by the net inertia. Now, the overall inertia is going to be m1 plus m2, and the acceleration I got here, using what looks like the wrong numbers, is 1.18 meters per second per second. Okay, so the setup, works this way. It could be we got to go in and double check some of the numbers on this. Okay, good problem, right? Okay, that's, so any questions on this, stop by office hours, let's take a look and see where we are with that. Okay, we have been looking at frictional forces, both static and kinetic. We are ready to move on to kind of a different topic. So this is going to feel pretty different. We're going to be looking at circular motion. So we're back looking at kinematics. Now, when we did kinematics before, we did straight line motion, and then we did X, Y, and sometimes Z motion. Well, circular motion's kind of like multi-dimensional, but circular motion has a particular shape to it. It's circular, and that means that we can think in terms of a radius that defines the circle. So, you know, I always like to say if it's circular motion, there's going to be a center to the circle. So identify the center, we've got that right here. What this is showing is that when we have circular motion, that there's a, well, we're going to start off with a fixed value of r, where we actually complete circles, and r is not changing. We'll see once we've learned how the simplest forms of circular motion work, we can actually change things up a bit. But for right now, let's just stick with straight circles, pure circles, so circular circles. So let's use circular circles that are circular in shape, and that means that r is fixed. Now you'll notice they're calling this uniform circular motion, and that's also just to get started. So for us to get started, we're going to treat this as if the speed is always the same. It just keeps moving at the same speed, and that's not a requirement. We're going to find out for circular motion, we could be going around in circles, but it could be sometimes we're moving faster, and then we slow down, then we speed up. We can change velocities as we go around in these circles. Now, what that says then is if it's truly uniform circular motion, the speed here matches the speed here in magnitude, but not in direction. So that's why they're actually listed as two different velocity vectors. They're being measured at different times, and we're finding out that the components here, x, y, do not match the components there. So things are changing. This represents an acceleration. So even though v, the speed v, the magnitude is not changing, the direction is. And if the direction is changing, that tells us that components are changing, and that means we have an acceleration. Now, let's see how this would work. If we are following a circular path, then, point C is at the center, I come out a radius, and here I am at a location along the surface. The velocity is tangent to the trajectory. So when I draw that circular path, that is the path the object is following. It's kind of its trajectory, its course that it's following. And the velocity vector points right along the direction of the path. Now, as the path changes direction, the velocity vector also changes direction so that at every point, the velocity vector is going to be tangent to the circle. In this case, it's a circular path. Now what we can show here, there's a formula that gets used, and that says that there's an acceleration. What direction is the acceleration in here? If I'm traveling along at some velocity, if the acceleration were forward, that would say I'm speeding up. Okay, so here I am at point A, traveling in that direction, at least at that instant. And so I've got a velocity right at that instant pointing forward. If the acceleration were forward, I would be speeding up. Well, I'm not speeding up. What if the acceleration were backwards? Well, that would tell me I'm slowing down. I'm not slowing down. I'm changing the direction. The direction is what's changing, not the speed. And so these circular motion, when I have circular motion going on, the acceleration is in the radial direction. In fact, it's in a radial direction pointing back towards the center of the circle. Now that might seem a little funny at first, but let's think about it again. If I'm going along and I have an acceleration forward, I go faster in that direction. If I'm walking along and I have an acceleration backwards, then I'm slowing down. Those are results of forces. So what is it that would create an acceleration forward? Well, that would be a force in the forward direction. What would create an acceleration backwards? That would be a force in the backwards direction. So to speed me up, I want a force in the direction I'm traveling. To slow me down, I would want a force opposite the direction I'm traveling. But to turn to the side, let's say I want to go make a right turn here, I am going to need something pulling me to that direction. Something has to pull me off course. You know, my intention was to go in a straight line. Objects left to themselves just keep going in a straight line. But if there's a sideways force, I will get pulled to the side. Now, if the sideways force continues to be sideways, then I end up in circular motion. If, you know, the sideways force is constant, and it continues to just pull me off to the side with a fixed curvature, I'll end up looping around in a circle. And so the direction of the force is towards the center, and the acceleration is also towards the center. What's happening here is I'm going along, I have a Vx, but I now have a force in the y direction. That's creating an acceleration in the y direction. I'm starting to pick up speed. So I get pulled to the side. So let's take a look at these vectors. If I take 2 points along the curve, point A and point B, which are separated by an angle delta theta, if I take a look at the two velocity vectors and I pick those velocity vectors up and I move them over to a vector diagram, and that's an important thing to do. So you've got to be able to pick up a vector from different locations, this velocity here, bring them together, and what we can show is, well, whatever velocity 2 is at that later time, it is equal to whatever the velocity was at the earlier time plus delta v. So this is maybe our first example, of delta v's that are actually perpendicular to the velocity itself. They're not in the same direction. The delta v's are in a different direction. Now, why is delta v so important? The direction of delta v is the direction of the acceleration. So if the delta v is sideways, which it is, I'm picking up speed in the sideways direction. That's the direction the acceleration is in. So I can take the delta v, divide through by delta t, and that will give me the acceleration. In the limit, where the time intervals become really small, it's a derivative, right? So I'll end up with the acceleration, again, written as the time derivative of the velocity, but it's in vector form. And so that means I'm keeping track of both x and y components here. And for circular motion, what we find is if I take this diagram, which is this triangle here, which has r on this side and r on this side, and it is it's an angle delta theta. This diagram with my two velocity vectors looks similar to my diagram with the two position vectors. I think I have another diagram here. Theirs looks so nice, but there's a couple things I want to include. and that is position vector 1 and position vector 2. So they didn't draw these as vectors, but I'm going to do that. And then delta r is going to be in this direction. If delta r is a really short time period, if it's a delta r over a short time period, then I can treat that as dr. So now we'll just call that an infinitesimal. The angular separation here is going to be d theta. When I look at the velocities at point 1 and 2, same as the page before, I'm going to get dv that's perpendicular. So what's interesting in circular motion is that dr is perpendicular to r, and dv is perpendicular to dv, and since for an angle of d theta that we travel through, the velocity vector shifts by that very same d theta. These are similar triangles. So this triangle of dr, d theta is similar to dv, vv, d theta. So even though this is v1 and this is v2, remember we're traveling at the same speed, so v1 magnitude, oh, here it is, v1 magnitude equals v2 magnitude. We'll just call those sides v. r1 magnitude equals r2 magnitude. We'll just call that distance r. And so if I look at d theta here, d theta is equal to, in the limit, dr divided by r. And d theta from that diagram is dv over v. Now dr is equal to v dt, and dv is equal to a dt. So if we do the ratios here, when circular motion is occurring, a is to v as v is to r. I hope you guys like ratios. Ratios show up all over the place, and this is a nice geometric derivation that tells us that for circular motion, a is to v as v is to r. Those things are equal. Well, what that leads to is this formula. This is the way it's usually written. A is equal to v squared over r for circular motion. But again, I kind of like the a is to v is to r. So I've written that in and highlighted that as another way to think about this. And kind of remember the derivation. For years I had looked at these diagrams and they didn't make sense to me, and suddenly one time I was going through looking at it and then it made sense. So again, going back over things can be useful. So this is going to become our fundamental kinematic equation for circular motion. Notice we have not brought forces into this discussion so far. I mentioned them as we're going to need a force to have circular motion occur. Without forces, objects are going to go in straight lines. If I'm going to go in circles, I'm going to have a force, and it's going to have to be off to the side and pulling me to the center. But this is pure kinematics. For something going around in circles, this is the relationship. Now what's also interesting is, even though we solved this with kind of the assumption of uniform circular motion, it still works point by point. It works as an instantaneous formula, which is a nice feature. So even when we go on to the case where, well, what if we're not traveling the same speed at b? Well, at each instant, at each position that we go through, the instantaneous acceleration is given by the instantaneous velocity squared divided by the instantaneous radius. So that works instant by instant, minute by minute. So let's try this. I guess here's our diagram then. So we've gone in and said, here's the kinematics. The acceleration that we have now is called radial, or it's referred to as centripetal. And it points towards the center of the circular motion. Because, hey, if I'm going along in this direction, how do I have to alter my velocity to stay in a circle? And I have to alter my velocity by tipping the velocity in that direction. So a little bit of acceleration tips the velocity, and then a little more acceleration tips the velocity again, and then we end up completing a circle. So it's a nice diagram because it's showing at two different locations where the acceleration would be directed and where the velocity vectors would be directed. And hey, it turns out accelerations can be perpendicular to velocities. So they can have whatever angle between them that we would want, for a given situation. All right, so here's some numbers that we can put into a formula and see if this see what this works like. So we have a ball. We have this 150 gram object, this spherical object, at the end of the string, and it's going around in circles. And it's a horizontal circle with a radius of 60 centimeters. So this is like a top view. We're at the top, staring down, watching this ball go around in circles. Okay, so here are the circles the ball's going around in. What's the centripetal acceleration? We go, well, I think we can answer that. So here's kind of a drawing. Here is the circular motion going on. Here is the object. It's got a mass m, but I don't think we need that for this problem. We'll probably need it later on. So here is the object. It's got mass m. R, we're going to measure from the center of the circular motion out to the circle. The v is going to be tangential, and the acceleration is going to be pointing right back at the center. So I like that. I kind of like that setup where v is perpendicular to r and a is perpendicular to v, and the a ends up pointing right back at the center of the circular motion. Now I wrote down the given information. The mass here, 150 grams or 0.150 kilograms. The radius, I converted it into centimeters, so I guess we need to convert it back into meters because we'd like to stick with standard units here. Now, the formula that we had derived said that the acceleration for circular motion, the acceleration can be calculated, a is to v is to r, so a can be calculated as v squared over r. So we got to find out what v is. We know what r is. R was given 0.60 meters. V is going to be a distance divided by time. So the distance that we're going to travel here is 2 pi r divided by t, and the t, they told us, we got to go back and get more information here. I didn't read the problem carefully, so I got to go back and read it carefully this time. I did not read this sentence. The ball makes exactly 2 revolutions. So it completes this motion exactly 2 times in 1 second. If that's 2.00 revolutions, I guess that's got to be 1.00 seconds. What's the centripetal acceleration? So always read the problem carefully. That's key. Let's see, and that's why I got a factor of 2 here. So the distance it travels is going to be 2 complete circumferences during 1 second. I ended up with a speed of 7.54 meters per second. So I can plug those in. So for v, I'm putting in 7.54 meters per second. I got to square that one. The radius is given as 0.60 meters, so I don't square that one. The meters cancel. One of the meters cancels, but I have an extra meter plus 2 factors of seconds. That is going to give me acceleration units. The units work out. They have to, and they do. So putting the numbers in, the acceleration here is it's pretty big. So let's think about this. We need to stop and so a 60 centimeter. Now that was a radius, not a diameter, right? And it says radius. Okay, so I think we got that part correct. So 60 centimeter radius would give us like 120 centimeter diameter. So we're looking at circles that go like this. And we have to complete those 2 times every second. So 1, 2, 3. So it is pretty fast. So we have to make our way all the way around that. We have to travel that 7.54 meters every second. And so twice a second we'd have to, so that's, it's a pretty big acceleration, right? That was my concern, is I'm looking at that acceleration and I thought, wow, that's like 10 times the acceleration due to gravity. It's like 10 Gs if you were being whirled around at this rate. And, but that's what it works out to be. So that is a pretty large acceleration that we have ended up with. The velocity is pretty fast and the radius is fairly small, and we're getting a lot of acceleration for that calculation. Okay, let's bring in some forces. So here we've got the moon, centripetal acceleration. Maybe we don't have forces yet. I think it may still be more kinematics that we're making our way through here. So we're going to assume the moon's orbit is circular. It's not quite, it's a little elliptical. So let's assume that the moon's orbit has a radius of 384,000 kilometers, and the period of the moon's orbit is 27.3 days, and find out what the acceleration of the moon is towards the Earth. All right, so here's the diagram that I've set up. We're looking at the acceleration of the moon towards the Earth. Now, one thing that's kind of interesting here is we're assuming that the Earth stays right at the center. Now, the Earth and the moon, the Earth's like 80 times the mass of the moon, but the moon's a good-sized moon. If you look through the solar system, for example, there's like 7 large moons, is that right? It's like Jupiter's got 4 of them. Saturn's got a very large moon. Neptune, I think, has a large moon, Triton. And then Earth. So given its size, Earth's moon is pretty big. Venus doesn't have any moons. Mars has a couple of really tiny ones. So in some sense, you could almost treat the Earth-Moon system as kind of a double planet system, right? So to have the Earth just sitting motionless, that's going to be a bit of an approximation, but we're going to do that in any case. But a better, more careful analysis would have the Earth and the Moon both orbiting a center of mass, which would be much, much closer to the Earth, like 80 times closer to the Earth than it is to the Moon. But still, that would result in the Earth wobbling a bit as the Moon orbits. In any case, we're going to have the Earth sitting still. Now, where's the center of the circular motion? Well, it's on the center of the Earth, given the way we've set up the problem. And then the center of the Moon. So it's center-to-center measurements. So there's always this tendency, I'm not sure why, to think that r, the distance, is measured from the surface to the Earth, and it's not. It's not measured surface to surface. It's measured center to center, because what we want to follow here is, well, first of all, the circular motion of the moon. And if we're taking an object, the moon's a big object, relatively, and so what we want to do is follow that center of mass of the moon as it orbits. So we want to use the center of mass to represent the average location of the moon. That's the distance we want to work from. And if the Earth is placed at the center of a circle, well, the center of the circle would be the center of the Earth, not its surface. So definitely, and so astronomically, when I'm looking at a table of astronomic data, and it says the Earth is this far from the moon, that's center to center, because that's the number that goes into all of our formulas. It's not surface to surface. So make sure you're thinking in those terms, and when you're drawing your diagram, that's the perfect chance to kind of reinforce that notion. We're going center to center, the Earth and the Moon, and that distance given to us is 380,000 kilometers. And yes, the numbers you get out of the table are going to be center to center distances. That's the standard. And that goes right into our formula, so that works out well. So that's 3.84, 10 to the 8th meters. Again, I can calculate how fast the Moon is moving in this orbit. Now we've used this formula a couple times, but we're coming back to it again. So 2 pi r divided by what we call the period. Now the period was given, let's go back. I just want to refer back to this. So the period here is 27.3 days. So I got to multiply that by 24 to get hours, and I got to multiply that by 3,600 to get seconds. So I'm getting the time in seconds for the Moon to complete one orbit, and that is working out to be 2.36 10 to the 6th seconds. So that's how many seconds it takes for the Moon, again, to complete one orbit and get back to the same place in its orbit where it started out. So the velocity that we come up with, and this is kind of, these are kind of fun numbers to think about. So the Moon's orbital velocity around the Earth is 1,023 meters per second. That's pretty fast. That's like if we use those conversions that we did back in chapter 1, that's going to be like, what, 2,300 miles an hour for the Moon's orbital speed. It's pretty good speed. And if you remember, we said Earth's orbital speed is like 67,000 miles an hour. So Earth's orbital speed, and the Moon, it's not just the Earth that's orbiting the Sun, but it's the Earth-Moon double planet system that's making its way around the Sun at 67,000 miles an hour. Anyway, getting back to this, I got a velocity of 1,023. I've got to square that according to my kinematic formula and divide through by r. Now the speeds are really fast, but the distance is really fast too. And what we're finding is the acceleration of the Moon towards the Earth is not so big, right? 0.00272 meters per second. So the acceleration is kind of tiny. Now, just by not by coincidence, but if once we get into chapter 6, we're going to learn ways to calculate gravitational fields. And so, what is the value of Earth's gravitational field at the surface of the Earth? And Earth's gravitational field is 9.80 newtons per kilogram. What's the gravitational field of the Earth once we get way out here? Well, the gravitational field of the Earth gets weaker and weaker. But what we know is that the gravitational field of the Earth at the location of the Moon, that's what's creating this acceleration. The force that's holding the Moon in a circular motion instead of a straight line motion. The Moon would, left to itself, it would go in a straight line. But the Earth's gravitational field is exerting a force, and the gravitational effect equals the gravitational field. So the acceleration we have due to gravity, 0.00272 meters per second squared, equals the 0.00272 newtons per kilogram. Again, we'll come back in chapter 6 and look at more of these examples of calculating gravitational force. All right, good example to bring in a lot of conceptual stuff in that example. So here's another interesting example. How do we create, effectively, how do we create something that would be equivalent to really large gravitational fields? And we can actually do this through circular motion. This is a centrifuge So we're taking, there's some biological stuff in here, and we're going to spin this. So it's a collection of, we took a bunch of cells from some sample and we lysed the cells, and we're taking the cell contents now and we're spinning them. And the idea here is to separate things out. The assumption is if we start spinning all this stuff that we took out of the cells, some of it will be more dense and some will be less dense. If we just set this in a jar and come back the next day, it hasn't separated very well. The materials tend not to separate into layers very well. But if we accelerate them, if we flip them circularly, it turns out that the denser objects, everybody's trying to go in a straight line, right? The denser objects will end up making their way to the outer regions of the tubes, of the centrifuge tubes here, and then we'll get lower and lower densities inward. So we set up a really nice density gradient. And again, for biological samples, this works great. Maybe the DNA lines up at one layer and some of the proteins line up somewhere, maybe the fats line up, the lipids line up at different locations. So it's a way where you can separate it out, and then you can go in and see if you can understand each one of those bands. You can put a needle in there and pull out that part of the sample and analyze it and see what that layer consists of. So anyway, just the idea that when we spin things fast, everybody throughout this tube is tending to go in a straight line, but instead they get curved. Now they can't all be at the bottom, and that means that the less dense stuff ends up, the denser stuff ends up, it's harder to pull the dense stuff towards the center. That stuff goes to the bottom. Okay, so it separates out by density. Here is an ultracentrifuge with numbers. So it says that we have a rotor, this spinning part of this ultracentrifuge. It's rotating at 50,000 revolutions per minute. Now we've learned how to deal with that. So each revolution is a circumference, and that's 2 pi r. A particle at the top of the test tube, starts out at the top, is 6 centimeters from the rotational axis. Find out what the acceleration would be. So it's not so much keeping track of how things separate, but rather it's just coming back and using circular motion kinematics formulas one more time here. So, okay, so I got something going around in a circle, and again, we got to calculate V, so that's 50,000 rotations, 50,000 circumferences in a minute. So that's 60 seconds, and that gave us a velocity of 314 meters per second. And the R value here is 0.060 meters. So it was a 6 centimeter distance from the center. We're measuring from the center out to this one location. That gives us a speed of 314. Plugging that into our acceleration formula, wow, this came out to be 1.6 million meters per second squared. 1.6 million. So you can see these centrifuges are really handy because they can create these enormous accelerations in a tiny space. So you can take the centrifuge, since it's spinning around in a circle, it just keeps cycling through the same. You can set it on a desk, right? So here's a centrifuge, I'm setting it on a desk, I'm putting some samples in there. I'm going to create an acceleration of 1.6 million meters per second squared, and it's all sitting there right on the table. It's not like I need a long track to get these objects up to a really large value of acceleration. I just spin them and they stay in the same location. Now they wanted us to, I think, let me go back and see. Again, I got to read the problem carefully. It says calculate the centripetal acceleration and calculate it in G's. Now, the G stuff is okay. I'm really more interested in just this number here, But if we do want to compare it in terms of gravitation, what we can do is say that the acceleration is some number. That's not a normal force, that's just a number. It's some number of gravitational accelerations. And so n then is a divided by g, and that says it's 168,000 g's. G's, that's a lot. Okay, so that's our ultra centrifuge. Now, questions on that? Let me pause a bit so we can think about what just happened here. So we've done a number of examples using this kinematic formula. So let's bring forces in. So we talked about this back in chapter 4. When we bring forces in, we now call this dynamics. So it's not just kinematics anymore, this is dynamics. So what are the dynamics of circular motion? For an object to be in circular motion, there's got to be a force. If there's not a force, the object goes straight. Now, if I've got something already spinning, like this, there's got to be a force. So the force here is directed towards the center. You've got to keep pulling it towards the center, otherwise it's going to go off in a straight line. So if we let go of this, you know, if this is spinning, and we let go right when it's here, and it's going to go off in that straight line. If it's spinning, and we let go when it's right here, it's going to go off in that straight line. We have to keep pulling it to the center if we want to keep it in circular motion. So how much force is that going to require? Now, for circular motion, this becomes kind of our go-to formula for kinematics. That tells us how the speed and the radius and the acceleration are all going to be related. This is the same. So we're going to go right back to Newton's second law of motion. The acceleration equals F over m. And so if we look at all the forces acting on that object, we can relate that to the mass and the acceleration. And here is the expression for the acceleration. And they're not kidding around. You can see they put a period in. So that, I guess it needed to be an exclamation point. Anyway, these are the same formulas that we've worked from before, but we're always going to need a force. The force is going to be in the direction of the acceleration, and that direction is going to be towards the center of the circular motion. So the force must be, we can see, if we stop and think about it, the force has got to be inward, like with a ball on a string. The string is pulling the object in. The object otherwise would go in this direction. If I got something going in this direction, but instead I would rather have it go in this direction, I pull it in that direction. So I got to pull it or push it in the direction that I want it to redirect its velocity. Okay, so it's the centripetal direction that we're looking at with this. Now, there's the forces that we looked at are called centripetal forces. Sometimes there's this confusion that forces, well, I guess this is the picture here. This is what doesn't happen. So if you take a look, and they've got this grinding wheel out here, so they've got this wheel spinning around very rapidly, and they're setting an object up against that. So these objects are in circular motion, and then because of the forces acting on it, the friction forces or whatever, there are little bits of the metal that are being broken off. And they're coming off and they're going in a straight line, right? They are not coming off and curving away from that path. They are coming off and heading off in a straight line. So that's one of the, it's a major misconception, right? That if you've got something spinning, something is pulling it to the outside. No? Again, if I'm going to curve off to the right, I need a force in the right direction. If I'm curving off to the left, I need a force off in the left direction. So that's what's going on with the circular motion. All right, here is, this has got some force diagrams and everything. So this is dynamics. So example 511, force on a revolving ball. So we've got this object, it's going around in circles and we're spinning it over my head, I guess, is where I should do that so the string doesn't wrap around my neck. Estimate the force a person would exert on a string to a 150-gram spherical object to make that object revolve in a horizontal circle. So the same radius, 60 centimeters, same object. Now before we never used the mass, this time we're going to need to because we're going to be going in and calculating forces. So again, the ball is making 2 complete revolutions per second. We're spinning this around. The acceleration was extreme on this. So here's what my diagram looks like. Here is the distance out, the radius of the circle. Here is the center of circular motion. Here is the force coming inward. The acceleration is in the same direction as the force. The velocity, though, is going to be tangent to the circular motion. These are the same numbers as before. This is the same number as before. How fast is it traveling? This is the same number as before, I hope. Isn't this what we got before? 94.7 meters per second squared. I hope we did this correct both times. So the only thing left to calculate is the force. That's the new part of this. So what force is this? And the force that we have here is, I'm gonna classify it as a tension in the string. So we've looked at tensions and strings and cables and whatever before. And so this tension is going to need to be able to take an object that's 0.15 kilogram and accelerate it at 94.7 meters per second squared. And that says that the string is going to need to maintain a tension of 14.2 newtons. That's how much tension I'm going to need in that string. And just a statement down here, that tension is required to make sure that the object stays in circular motion, otherwise it'll just go off into straight line motion. So that's it. That's the first example of calculating a force. That looks pretty good. Ooh, here's something that's more complicated. So now this is a little... Okay, first of all, we have circular motion. It's this spherical object again, revolving around the center, and the center of the circular motion is right here. Now, somehow what they've done, oh, maybe not so. Okay, I take that back. I was a little worried. I know that there are some examples where they, with the vertical circles, maybe I'm thinking of a homework problem, where they assume that the velocity is uniform the whole time. And it's not impossible to do that, but it's hard to get that to happen. So because of gravitational forces, the tendency is to pick up speed on the way downwards and then slow down here. Now, this actually is following that idea. So they're saying that, well, they changed the mass is the same as the previous examples, 150 grams, but they've changed the length of the cord. So the cord now is 110 centimeters, and the cord itself has negligible mass, and we're swinging this in a vertical direction. Now it says at the minimum speed, we want to find out what would be the minimum speed at the top for the ball to remain in circular motion. And then part B says, what's the tension at the bottom, assuming it's moving twice as fast. So it is moving at some speed at the top, and it's moving twice as fast at the bottom. So that sounds more reasonable, because it's a pretty simple setup. I've just got a string with a ball attached, and we're just going around in circles. So, but in order for this, the string's flexible. So what happens if it's not moving fast enough it won't make it to the top. The string will become loose and the ball will go into projectile motion. It'll just be free falling through the air. It won't depend on the tension. So what they're asking in point A is this, is what we seem to find when we do this, and I think, you know, most of you have probably done this. You pick up a ball or something on a string and spin it around, and what you find is if you spin it fast enough, then the ball will make these really nice circles, but if it gets to be too slow, again, the ball is not going to make it to the top. It's going to, the string's going to come loose, the tension's going to be gone, and the ball is going to go through projectile motion. So let's get a force diagram on this. I think that's what we need. So let's get a couple force diagrams. First of all, there's a force diagram at the top. Now at the top, there's a gravitational force down, and I'm going to say that there's a tension in the string. Now at the bottom, just for comparison, there is a gravitational force. Notice the gravity at the top and the bottom, they're both pointing downwards, but the tension changes direction. At the top, the tension is downwards, but at the bottom, the tension is pointing upwards towards the center of the circular motion. And since it's a circle, we have a radius and it's the same value throughout. The velocity here, v1, tangent, and then it comes down, picks up speed, and then velocity 2 is here. Now there's going to be, if it's in circular motion, there's going to be an acceleration at the top, a1. There's going to be an acceleration at the bottom, a2, and those accelerations will be towards the center. So we've identified the forces, we've got their directions set up on these two force diagrams, one at the top, one at the bottom, and let's write down, so here is the minimum speed, let's write down our formulas. Now, what condition would let us know that we have reached minimum speed? So if we're spinning this pretty fast, there will be tension in the string at the top. We will need the tension to help maintain circular motion. Gravity by itself will not maintain circular motion, so we're going to need some tension also. So that's what's going on when we have these nice circles and we're spinning this thing pretty fast. As we slow down, what happens is the acceleration becomes less and less, and at some point we don't need any tension in the string. So the condition at the top, such that the spherical object, such the mass goes through a circle, maintains a circular path, is that the tension just barely goes to zero at the top. And then on either side of the top, the tension picks up again. So the tension just barely goes to zero at the top, and then it picks up again off to the side. Now, that means the velocity isn't zero. You know, there's got to be some speed at the top in order for that to happen. If the velocity stops here, the ball just falls, right? So let's write in our kinematic formula. This is telling me how the acceleration and velocity and radius are all related. And then what will happen at the top then, if the tension has gone to zero, then the net force is coming from gravity. So it turns out, at minimum speed, all of the acceleration is entirely due to the gravitational force alone. It's not due to the tension. So we can divide through by mass, the masses cancel out, and it says, in order to just barely maintain circular motion at the top, the acceleration needs to be equal to g. It needs to be that large. That's the minimum value that the acceleration can be and still have it go through circles. Well, we can flip this equation around then. We can say that v1 squared over r, we can set that equal to g, and then say that v1 is g times r square root, and then we can plug the numbers in. So the numbers here were 9.8 meters per second squared times 1.10 meters square root. It says that that's our minimum speed. The minimum speed at the top is the speed that will give us an acceleration that matches the gravitational field. Now, that's the speed at the top. So we're spinning this thing so that we just barely get through the circle at the top. The speed at the bottom is twice as much. So what effect will that have? Well, let's go back to this formula. So if I double the velocity, but I keep the r value the very same, how much will the acceleration go up? And the acceleration is going to go up by a factor of 4. If I double the velocity in that formula, v gets doubled, that's a factor of 2 squared, that's going to give me a factor of 4. And so the acceleration now needs to be 4 times as large, or 4 times g. Now, how much tension will there be in the string at the bottom? At the top, the tension was equal to 0. So we started this whole discussion by reasoning that at the top, the tension was equal to 0. For that, we needed a minimum speed. We've now used that to determine what the speed will be at the bottom and what the acceleration will be at the bottom. And so we can come back to this formula and say whatever the acceleration is at the bottom, it's a result of these two forces. Now, why is there a plus sign on tension and why is there a minus sign on mg? Okay, and so tension is in the direction of the acceleration, mg is opposite to that, and that's what's going on. When we solve for this, then the tension becomes mg plus ma2. The tension here then is given by mg. A2 we determined was 4 times g. So the tension's got to be 5 mg's at the bottom, and that gives us 7.35. I just noticed that I think we're running out of time here. So let me check real quickly. We're over a few minutes, so we'll stop. So I'm going to stop here, and then what we'll do is we'll pick up from this example. This is a good example that we could start from next lecture. So we'll come back and review this, and then we'll be moving on. All right, any questions? Stop by office hours.